Welcome to Paper Trail, where we make academic research accessible and engaging. Let's see what the evidence says.
We often hear about AI models, particularly large language models, having a temperature setting. The common understanding is that if you set this temperature to 0, you get deterministic, reproducible output. The same prompt should yield the exact same response every time.
That's the widespread assumption, and it's a very intuitive one. Zero temperature implies zero randomness, right? But what the research suggests is that this exact measurement is more of an illusion. Even at a temperature of 0, these models can still exhibit stochastic behavior. Effectively, they can still hallucinate randomness.
So even when you're explicitly telling the AI to be completely predictable, it might still give you a slightly different answer each time? That's a significant claim, especially for applications where reproducibility is critical. What kind of randomness are we talking about here? Is it subtle, or could it lead to completely different outputs?
It can range from very subtle variations, like slight changes in phrasing or word choice, to more significant shifts in the generated content over multiple runs, even with identical inputs and the temperature set to its absolute minimum. The paper essentially argues that the promise of perfect determinism at 0 temperature is fundamentally unachievable due to a confluence of underlying factors.
Could you unpack this concept of temperature first for listeners who might not be familiar with it? What does it actually control in an AI model?
In the context of large language models, temperature is a hyperparameter that governs the randomness of the output. When a model generates text, it essentially predicts the probability distribution of the next word given the preceding sequence. A higher temperature value, say 1.0 or more, makes the model's choices softer. It increases the probability of selecting less likely words, leading to more creative, diverse, and sometimes less coherent output.
So it's like turning up the creative dial. The model is encouraged to explore more unusual word choices.
Precisely. And conversely, lowering the temperature makes the model's choices harder. It prioritizes the most probable next word. At a temperature of 0.001, for instance, it becomes much more conservative, sticking very closely to the highest probability sequence. The theoretical idea behind setting temperature to absolute 0 is that it should always pick the single most probable token, making the output identical every time.
And yet, the research suggests this isn't happening. Even when it should be picking the single most probable token, there's still variability. What are the core reasons identified in the paper for this persistent randomness?
The paper highlights several key contributors. One major factor is the inherent non-determinism in floating-point arithmetic operations, especially across different hardware architectures or even different runs on the same hardware due to how computations are scheduled. When you're dealing with billions or trillions of parameters and calculations, even minute sub-epsilon differences in intermediate floating-point results can cascade.
So it's not a bug in the AI's logic, but rather a consequence of how computers actually perform math at a very granular level, like the tiny discrepancies that can emerge when you add a long list of numbers in a slightly different order?
Exactly. Think of it like this. If you have a huge spreadsheet with millions of calculations and you run it on 2 slightly different versions of Excel, or even the same version but on different machines with different processors, the final result might have a tiny, almost imperceptible difference in the last decimal place. For most everyday tasks, this doesn't matter. But for an AI model that's picking the most probable word from a distribution that might be extremely close, that tiny difference can be enough to tip the scales between 2 or more words.
And the model then follows that slightly different path, which can diverge further down the line. What else contributes to this?
Another significant factor is parallel processing. Modern GPUs, which are essential for running these large models efficiently, execute operations in parallel. The order of these parallel operations is not always strictly defined or guaranteed to be identical across different runs. This can introduce slight variations in the accumulation of gradients or intermediate states.
So if you have 1,000 small calculations that need to be done, the GPU might do them in sequence A, then B, then C one time, and then C, then A, then B the next time. And that slight reordering can subtly alter the overall outcome.
That's a good analogy. While the mathematical operations themselves are deterministic in isolation, the timing and ordering of these operations, especially reduction operations, like summing up results from many parallel threads, can lead to minute variations in the final numerical representation of the probability distribution. It's not a logical error, but an artifact of highly optimized parallelized computation.
That sounds like a really difficult problem to solve, almost a fundamental limitation of how these complex systems are built and run. Are there other architectural or sampling-related issues that play a role?
Yes, absolutely. The paper also points to specifics in the implementation of sampling methods. Even with a theoretical zero temperature, models still often employ some form of argmax function, which selects the token with the highest probability. However, if multiple tokens share the exact same highest probability, or if their probabilities are numerically indistinguishable due to floating point precision, the tie-breaking mechanism can introduce non-determinism.
So if the model calculates that apple and banana both have a 0.352789 probability of being the next word, and that's the highest probability, which one gets chosen? Is there a random element there, or is it system-dependent?
It's often system-dependent. Different libraries, different versions of the same library, or even different hardware might resolve that tie in a different arbitrary way. Some might pick the token with the lowest index, others the highest, and some might effectively pick one quasi-randomly if the underlying implementation doesn't guarantee a consistent tie-breaking rule. The paper emphasizes that this is particularly true for less common tokens, which might appear in sparse regions of the probability distribution.
This all sounds incredibly technical, but the practical implications are quite profound. If you can't guarantee deterministic output even at zero temperature, what does that mean for critical applications of AI? Think about code generation or medical diagnostics or legal document drafting.
That's precisely the central concern the paper raises. For fields demanding high reliability and verifiability, like scientific research, financial modeling, or safety-critical systems, the lack of absolute reproducibility at zero temperature poses a significant challenge. It means that an output you get today might not be exactly the same as an output you get tomorrow, even under identical conditions. This makes debugging difficult, and auditing or validating model behavior becomes a much more complex task.
So if a software engineer uses an AI to generate a piece of code, and they get one version, and their colleague runs the exact same prompt and gets a subtly different version, that could introduce errors that are incredibly hard to trace back to the model's non-determinism.
Exactly. It undermines the very expectation of a predictable tool. For instance, if an AI is used to generate test cases for software, and those test cases vary slightly each time they're generated, it complicates test coverage analysis and the consistency of the testing process. The illusion of exact measurement means users need to be aware that some degree of stochasticity is always present, even when they've tried to eliminate it.
This also brings up questions about fairness and bias. If slight variations can occur, could those variations inadvertently introduce or amplify biases that are then hard to detect and address?
That's a valid concern, though the paper doesn't delve deeply into bias specifically related to this type of non-determinism. However, one could speculate that if the tie-breaking mechanisms are not truly random, but instead systematically favor certain outputs, perhaps due to memory layout or system-level specifics, it could introduce subtle, persistent biases that are incredibly difficult to diagnose because they aren't tied to the model's trained weights or data in an obvious way. It would be a systemic bias rather than a data-driven one.
Fascinating. So what steps can be taken, or what understanding should users and developers have to navigate this inherent randomness? Is there a way to truly achieve determinism, or should the focus be on minimizing the variability?
The paper suggests that truly absolute determinism across all environments and runs might be an unattainable ideal. Instead, the focus shifts to understanding and managing this variability. One approach is to meticulously control the computational environment, using fixed seeds for any random number generators that might still be implicitly involved, standardizing hardware and software stacks, and using specific libraries or frameworks that offer stronger guarantees for deterministic execution where possible.
So it's about tightening all the screws you can tighten, even if you know a few might always be a little loose.
Precisely. Another recommendation is to implement robust testing and validation strategies that explicitly account for potential non-determinism. This might involve running the same prompt multiple times, even at zero temperature, and analyzing the distribution of outputs to understand the typical range of variations. For critical applications, this multi-run approach becomes a necessity, not just a luxury.
It's almost like the scientific method, where you repeat an experiment multiple times to ensure your results aren't just a fluke, except here, the experiment is a single AI prompt.
A very apt comparison. It underscores that even with advanced AI, we're still dealing with probabilistic systems, and understanding their inherent uncertainty is key to their responsible deployment. The paper really pushes for a shift in mindset. Instead of expecting perfect determinism, we should anticipate and characterize the residual randomness.
This also raises questions about model versioning. If a model update includes changes to the underlying libraries or even the compiler used, it could inadvertently introduce new non-determinism even if the model weights themselves haven't changed.
Absolutely. The paper implicitly highlights the challenge of maintaining model integrity and reproducibility over time. A simple library update that changes how floating point numbers are handled or how parallel operations are ordered could alter the output of a zero-temperature model, making it difficult to compare results across different versions or even different deployment environments. It makes the exact measurement even more elusive when you factor in the dynamic nature of software ecosystems. It's a call for greater transparency and scrutiny in how these models are deployed and managed in production environments.
This has been a really enlightening discussion about a subtle but critical aspect of AI. So, to summarize some key takeaways from the research, first, the idea that setting an AI model's temperature to zero guarantees deterministic output is in fact an illusion.
That's right. The paper clearly demonstrates that inherent non-determinism persists, challenging a common assumption among users and developers.
Second, this residual randomness isn't necessarily a bug, but rather a consequence of fundamental computational practices, particularly floating-point arithmetic precision issues and the non-guaranteed ordering of parallel processing on modern hardware.
And also specific tie-breaking mechanisms in sampling when multiple tokens have equally high probabilities. It's a confluence of factors at a very low level of computation.
Third, the implications are significant, especially for high-stakes applications where reproducibility, reliability, and auditability are paramount. It means we cannot blindly trust single outputs from even deterministic AI runs.
Correct. It demands a more rigorous approach to validation and deployment, acknowledging that some level of variability is always present.
Finally, understanding this illusion means shifting the approach. Instead of chasing perfect determinism, we need to focus on characterizing and managing this inherent variability through careful environmental control, robust testing, and a multi-run analysis of outputs.
It's about moving from an expectation of exactness to an understanding of bounded uncertainty.
Given all of this, what's one question listeners should keep in mind as they interact with or build systems relying on AI?
How much variability are you truly prepared to accept in your AI's outputs, even when you've tried to eliminate it?
And for those developing AI tools, how do you communicate the inherent uncertainty of your model's outputs to users, even when your settings suggest absolute certainty? That wraps up this episode of Paper Trail. Join us next time as we dig into more research worth talking about. If you liked what you heard, share it with a friend.
Keep reading the fine print.